Generou. I'm an assistant professor for 3 more weeks in chemistry at UCR. My lab does protein homeostasis. We make methods to measure the misfold. I'm going to chair this afternoon session. For our first speaker, we're honored to have Wout Bittremieux from Antwerp. Now, if there's one thing that we learned from many of the talks today, hopefully there's more than one, but one of the things is that it's often hard to identify what we're looking at mass spec. And I think it's fair to say that Wout spent most of his career helping solve that problem. He got his PhD developing computational proteomics methods. He continued on with Bill Noble over at Washington, coming up with better computational tools to be able to match the spectra. And then I guess deciding that peptides were too easy, we went on to do the same thing with metabolomics.
Exactly.
Down with Peter Dorstein. And then today he's going to tell us what he's been doing in his independent lab.
Thank you for that very kind introduction. All right, so in my lab, we focus on analyzing repository scale data, really going for millions of mass spectra. And actually, I'll start a little bit with a story that started at UCSD and Peter's lab, and I'll continue with how we're building on that in my own research. The focus or something.
No talk would be complete without a technical glitch, particularly by computer scientists.
All right. When you look at this photo, it might not immediately be obvious what you're looking at. But this is actually a close-up image of a single grain of sand. And similar as an individual spectrum, even though that might be your key metabolite that you're interested in, it's only going to give you a limited amount of information. Instead, you need to zoom out and look at all of the grains of sand or all of the spectra within an individual experiment, which is here on the Southern California beaches, which I do miss. But you can zoom out even further and look at different experiments on the same system and get an even bigger, more holistic image of your specific research question. And in the end, can zoom out even further and consider all of the data that is available in these public repositories to really get the deepest amount of information and the insights that you can get. And just like this image, we needed to develop these modern, super powerful telescopes, such as the James Webb Telescope. In my lab, we're developing the computational tools to give us insights at such massive scales. One of this project that I started in Peter's lab was the nearest neighbor suspect spectral library. So this was published late last year, but it has been around for a little while, so you might be familiar with it. For the people that aren't, I'll give a brief introduction. We start from molecular networking, and in molecular networking, all of these nodes correspond to individual MS/MS spectra. They're annotated with their precursor MZ, and the edges between the different nodes are also annotated with their precursor mass differences. Now here, the square node indicates that this spectrum could be annotated using spectral library searching. And in this case, the spectrum corresponded to acetylcarnitine. For the round nodes, we didn't get a match using spectral library searching. So, you might say we don't know anything about these spectra. However, we do know quite a bit of information about them. We know that they're related to acetylcarnitine because they're connected via an edge in our molecular network. And we know their corresponding precursor mass difference. So you could actually say that, for example, this green node, it's and what we call it a suspect related to acetylcarnitine with the addition of 3 carbons and 6 hydrogens, because that matches our delta mass difference of 42 Dalton. And similarly, this information could actually be enough for an expert to generate a structure hypothesis. For example, for the blue suspect, we're looking at the spectrum and potentially validating it with synthetic standards, you might be able to discern that this was actually propionyl carnitine. And so we did this approach on repository scale data on GMPS. We took data from over 1,000 different data sets on GMPS and used molecular networking first within each data set separately, and then across all of the data sets combined to build a repository scale molecular network. And this is actually a crucial aspect of this work because now you can find these patterns across data sets. For example, a metabolite that might be present in plants or animals that are consumed as foods. You would have the original metabolite in your original organism, but then you might have a metabolized version of it within humans after it has been consumed. If you would look only at each experiment, the data from each experiment in isolation, you wouldn't find the connections between these related versions of these molecules. But by networking at the repository scale, now we were able to find all of these connections. And so we did this for 1,300 compatible data sets on GMPS, over 500 million MSMS spectra. We built our global molecular network from it, hundreds of thousands of nodes, millions of edges, and then we extracted these suspects that I introduced a little bit previously from it, almost 90,000 new suspects, also covering over 1,000 different modifications. And so even though these suspects, they don't provide exact identities of these molecules, they do give you a lot of extra information. So here on the top, we have a reference spectrum for hexanoyl carnitine with the structure here indicated to the right of it. And below it, we have a suspect spectrum for hexanoyl carnitine with a loss of, with a mass difference of 2 mZ. Now, you see very nicely that both spectra have this characteristic acyl carnitine fragmentation pattern with both the neutral losses as indicated by the shaded boxes and the fragments as indicated by the colored fragments. And so even though we don't know the exact molecule that the suspect corresponds to, we have a lot of information and we could actually reason about this, use some chemical knowledge, mainly by collaborators, not by me, because I don't know that much about chemistry. But looking at it, might actually determine that this is then hexanoyl carnitine, where one of these bonds here is single bonds is replaced by a double bond. We don't know which one, so we don't know which exact molecule it is, but we do have a lot more information than if the spectrum would have been completely unknown. And sometimes we can go even further. For this other suspect related to hexanoyl carnitine, we now see that there is a mass difference of 12, approximately 12 MeV. You might expect that this is the loss of a carbon, but we have exact mass information, so it's slightly more. So instead of the loss of a carbon, it's actually the 3-hydroxybutyrylcarnitine. carnitine. And really, we were able to look at the spectra in detail, and there's like this tiny light blue peak next to the red one, which is characteristic for a 3-hydroxy acyl carnitine, which kind of provided the structural hypothesis of 3-hydroxybutyrylcarnitine. And then Mauricio actually confirmed this based on synthetic standards as well, which got like a cosine similarity of 0.999. So pretty much confirming this annotation. And so if we use the suspect library, in addition to all of the GMPS community spectral libraries for annotation using library searching, we do get, on average, a 2-fold increase in the spectra that we're now able to interpret. And we first did this for the 1,300 data sets that were included during compilation of the suspect library, and we got this nice increase. But then in the meantime, there were also 72 additional data sets that were deposited to GMPS that we used as like a independent test set. And again, we saw like this very nice 2-fold increase of the spectrum annotation rate, really confirming the benefits of the suspect library. So that's what we've done previously. Now, I want to take a brief step back and think a little bit about all of the computational steps that went into the creation of the suspect library. So we have this massive global molecular network, 13 million edges, but how did we get there? Well, there's a few different steps that we need to go through. First one is that we do clustering to combine different spectra that correspond to the same compound and reduce data redundancy. Next step is annotation, using spectral library searching to provide these initial annotations that are used to seed the molecular network and from which the suspects are derived. Then we do molecular networking among these spectra. And finally, we propagate identifications between pairs of annotated and unannotated nodes. So this is at a high level, the different computational steps that are necessary. And so we were thinking, okay, the suspect library, it's a very valuable resource, these 90,000 new spectra that we didn't have previously. But can we optimize all of these different steps to improve these results even further? And I think that we can. The first thing that we looked at was improving clustering. So clustering is really essential. It's an essential pre-processing step prior to molecular networking. This is a little bit of a toy data set for 1,400 acyl carnitine spectra that were extracted from GMPS using MassQL. And if you just build a molecular network from the raw spectra themselves, it looks a little bit like this. You know, it's all acyl carnitine, so it's all gonna kind of cluster together or, you know, be joined, and then we have a few singletons, and basically like this big hairball in the middle. It's not super interpretable. Instead, that's why we use clustering, right? To remove repeated observations of the same molecule. Now, GMPS typically uses MS cluster on the back end, which uses a greedy approximation of single linkage hierarchical clustering. And so we started evaluating what if we use different clustering algorithms instead. And on this data set, we evaluated both different types of hierarchical clustering and density-based clustering. And these are the results from hierarchical clustering, where you see like the yellow is kind of more or less what MS cluster does at this point. And then if we use different linkage functions, we do get improved clustering results, both in the number of clustered spectra on the left-hand plot, where, for example, if you look at below 1% incorrectly clustered, because that's what we're interested in, you kind of go from 83% of the spectra that could be clustered to 93% of the spectra that could be clustered if you switch to complete or average linking. And then completeness kind of measures into how many different clusters spectra from the same molecule are split. So ideally, you want to cluster as many spectra, and you also want all spectra from the same molecule to be present in a single cluster rather than split over multiple clusters. And so completeness also, you see that at 1% incorrectly clustered spectra, we do have a nice bump in completeness as well. So that means that the clusters are less fragmented than with single linkage clustering. And if you use this for subsequent molecular networking, we had our hairball initially. If we now use our optimized spectral clustering, the network will look a little bit like this. So, you know, it's still a lot of information, but it becomes a lot more manageable. And actually, we can quantify it a little bit better. And if we use DB-scan or single linkage clustering, which is kind of the current approach, we would get a network consisting of 336 nodes, 230 singletons, and the degree, which is kind of the number of edges, the average number of edges that each node has, a degree of 31. If we use our optimized hierarchical clustering with complete linkage, we significantly reduce the redundancy in this molecular network. We go down to only 216 nodes, a much smaller number of singletons, and 50% fewer edges for each of the nodes, because we have now removed these redundant edges. So it becomes much more interpretable. The next step in this process that we wanted to tackle was the molecular networking aspect of it. And so a key concept underlying molecular networking is that structural similarity is more or less mirrored by spectral similarity. Unfortunately, we know that in many cases, this is actually not the case. So these are two different molecules that are structurally highly similar to each other. They have a Tanimoto similarity of 0.95, and they differ in these three modifications that are highlighted. Unfortunately, if you take the spectra for these two molecules and you use the modified cosine similarity, it will be virtually zero. And why is that? Because modified cosine similarity can only account for a single modification. Here we have three modifications, so we'll have multiply shifted peaks that are not captured by modified cosine similarity. So you would never be able to connect spectra for these two molecules with each other in a molecular network. So instead, we started developing a neural network-based similarity score that kind of learns a spectral similarity that mirrors the structural similarity. So we started by compiling a large-scale training data set, because for these neural networks, the more data you have, the better. And so we used GMPS and NIS20. For our initial test, we limited to singly charged protonated adduct, which in the end gave us over 300,000 MSMS spectra and about 30,000 unique compounds. And we generated training data from these spectra by splitting on Merkle scaffold. So this is also essential for machine learning approach, that you have very clear distinction between the training and test data. So we used Merkle scaffold to split into training, validation, and test set. And then for training, we calculated 100 million pairs of spectra with their Tanimoto similarity. And we used weighted resampling to also upsample similar pairs. Why? If you take two random molecules, you compare them with each other, very likely they're going to be quite dissimilar. It's by random chance, it's much less likely that you'll have highly similar molecules. So we weighted that a little bit to have a balanced data set. And then we used this data set to train a deep neural network that kind of learns a score that mirrors the structural similarity based from the two spectra's input. So we use a transformer neural network, which is and we used a version of this architecture that we developed about two and a half years ago, and that we first used for de novo peptide sequencing and got like state-of-the-art results there. And so we used this type of architecture, build a deep neural network, a 5-layer transformer neural network that converts the spectra into embeddings, and then the cosine similarity between these two embeddings, and our model is called Simba. And so the cosine similarity between these two embeddings kind of mirrors the Tanimoto similarity between the corresponding molecules. And if we just look at some of our validation pairs or the test pairs, and we plot the modified cosine similarity between the corresponding spectra, and then the Tanimoto similarity between the molecules for these spectra, we see that there's actually a lot of pairs, even though they have high Tanimoto similarity. So then we would be looking here in the lower right-hand corner that still have very low spectral similarity. Instead, we want to go basically be there in the upper right corner. That's the region that we're most interested in. If we now look at our Simba score, now we see a very nice correlation between the spectral similarity and the cosine similarity. And if we compare it with alternative tools that have tried to do something similar, such as Spec2Vec and MS2 Deep Score, we also see that Simba outperforms them quite significantly. And this is an ROC plot where we kind of formulated the task as finding analogs if their Tanimoto similarity is higher than 0.7, if the model succeeds in that or not. The dashed line is kind of random performance. We see that modified cosine can do it to some extent, but not super great. Our previously neural network-based methods, such as Spec2Vec and MS2 Deep Score, are a bit better, but Simba is significantly better at finding these true analog matches. And so maybe here, going back to our previous example, we had our two molecules that are clearly similar to each other with a Tanimoto similarity of 0.95. Modified cosine couldn't find them, but Simba actually correctly predicts a very high similarity between these two molecules. And even though, and when we then interpreted the spectral match, kind of looked at all of different peaks, you do see that all of these substructures come back in both the top and the bottom spectrum, even though there are no directly matching peaks that modified cosine would be able to match. And so, these projects, we're still working on both optimizing and finalizing these two projects, the clustering and both the molecular networking. But we hope to then plug them into this entire workflow to generate our suspect spectral library, as well as some other ideas to improve the annotation part, propagation. We now have modifinder as well that could be used to get more information for these suspects. With those advances, we should be able to derive much more information from our repository scale data analysis and generate valuable structural hypotheses for previously unexplored spectra. And so this is, really a team effort in my lab at the University of Antwerp. These are students and postdocs that are working hard on these efforts. So it's really, credit should go to them. But I'm the one standing up here, so I'll also be happy to answer your questions now.
Questions for Wout?
Hi. Do you think if the difference between your predicted score and the modified cosine score is high, that could be an indication that there is more than one modification site?
Yes, exactly. Those are exactly the cases that Simba is able to find that the modified cosine is not able to find. Those relatively easy ones that differ in a single modification where modified cosine does work well, we do see that these are correct. And it's very hard to beat modified cosine for this well-defined case. However, for multiple modifications, we know that modified cosine doesn't work. So that's really the use case that we're trying to tackle.
Michael.
Yeah, so there's other neural net-based scoring things that you're comparing against. Yours is doing a lot better. Why is that?
It's a combination of a few different factors. One is this transformer neural network architecture. So yeah, we really developed it first for the de novo peptide sequencing application. But a big benefit of this is that previous approaches, how did they get a spectrum into a neural network? Well, you take your mass range, you bin it, and then you use that vector as input. There are two ways that you can do it. Either you use very small bins to capture your high fragment MZ resolution, but then your bins become super large, very hard to put these into a neural network, and they're also very sparse, so very challenging to learn from. So most of these approaches, like MS2 Deep Score and MS2 Deep Score particularly, they use one Dalton bin. So unit resolution, the data size becomes more manageable, but you lose your accurate fragment mass information. In contrast, the transformer neural network uses a positional embedding approach to directly encode the M over Z values at its native resolution without having to bin it. And that's one of the aspects where it's much better. In addition to this, this multi-head attention mechanism, and that's really the kind of the mechanism that powers all of these latest advances in generative AI, so ChatGPT, et cetera. These are all transformer networks that utilize attention. So similarly, this is really a big benefit of our approach. A downside of this is that, so these networks can be very powerful if you have a lot of data. So really the combination of also the GMPS and NIST data to really have a lot of data, these 100 million pairs that we're trained on, then allows our approach to really get this powerful performance.
A quick follow-up. How long would it take you to explain your encoding strategy to me?
Like 10 minutes with a few extra
I would love to hear
figures,
more.
but yeah.
I think in the interest of time, we'll move on, but there'll be a break later to ask similar questions. Thank you so much, Wout. So our next speaker is going to be Allegra Aaron from the University of Denver.